Okay, so let me, again, I'm going to go to the book and let me make sure. So hopefully, again, everybody can see the book page. Now, the one Jordan asked for was section 2.2, and this was exercise number 13A. Okay, so let's actually go to that section 2.2.
Yeah, can I ask something really quickly about it?
Of course, go ahead,
So
please.
I think I was able to figure it out on my own, just kind of like looking at it a little bit. I was just wondering, so if you have like the 3x plus 2a equals b, could you just use that equation to solve for x, and then like if you get x equals something, you just put that back into matrices and then like apply that sort of stuff, then you would get your x?
Sure. Again, if you let me, because I'm not looking, let me scroll to the problem
Oh
side.
yeah, sorry.
No, 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 don't be sorry. It's just I want to make sure I understand what the problem is even asking. So section 2.2, go to 2.3 and go back up. Quick way to get to the exercises in the previous section. Okay. Now you mentioned number 13. Okay. In number 13, the question reads solve for x in the equation. You're given a, b. I see. I see. Okay. So in part A, um, which is 3x equals 2a plus b. So what I would do is just like algebraic equation, you want to solve for x. Think of it as isolating the x. So you can subtract 2a from both sides, right? So I would say 3x is equal to b minus 2a, and then actually do b minus 2a. And let me, instead of just saying about it, let me actually go to my, uh, now that I have this first, allow me to write the problem, then I'll switch to my notepad here. So we're doing 2.2, number 13. Uh, okay, matrix A is the 3 by 2 matrix, negative 4, 1, negative 3, 0, negative 5, 2. And then matrix B, again, another 3 by 2, 1, negative 2, 4, 2, 1, 4. In part A, you're doing 3x plus 2a equals b. Okay, now let me make a switch here. Share OQCam. Okay, so now you can see what I was writing down. Okay, so to do this again, it's just like doing an algebraic equation. We're going to isolate x, right? So from this, I'm going to write 3 times matrix x is equal to b subtract 2a from both sides. Now, matrix b is going to be, um, let's see, what is matrix? Um, B is this one, negative 2a is this one. Okay, so I'm going to write this as 3x is equal to matrix B, 1, 2, negative 2, 1, 4, 4, and then negative 2 times a. So you're going to multiply every element of a by 2. So double up on everything pretty much. So that's going to be 2 times negative 4. So that's going to be negative 8, 0, twice 1, 2 times 5, 2 times 3, and 2 by 2 is 4. Okay. Now remember to add and subtract matrices. We're going to add, subtract elements in the corresponding positions, right? The corresponding elements, in other words. So when we do that, what are we going to get? We're going to get 1 minus, oh, and we need to mind that negative on the outside, which distributes to every element of this matrix. So to subtract 8, in other words, I'm going to add 8 to 1. So this one's going to be 9. 2 minus 0, that's 2. And then negative 2 minus 2, that's negative 4. And let's see, 1 negative, negative, positive. So that makes it 11. 4 negative, is positive. So that's 10. 4 negative 4 is 0. right? So that's going to be 3 times matrix X. True, that's what we got for part A. And then next step, what do you think we should do to get rid of the 3?
I think I like multiplied the other side by 1/3.
Perfect. Exactly. So we're going to multiply a third times both sides to isolate X. So that means divide 9 by 3. So that's a third of 9, a third of 2, a third of 4, a third of 11, and so forth. So there you go. And so there you go. That's how you would work the X. Does that help with your question, Jordan?
Yeah, thank you.
You're welcome. Okay. Again, anyone else with any questions on the homework, ladies and gentlemen, please ask if you have questions. And I'm gonna change my pen. I'm not writing well. Okay, so if everybody's okay, then should we go ahead with the new chapter then? Should we begin our chapter 3? Let's do that. So let me, again, I'm going to change my share real quick here. Okay, I'm going to go to a page of the book. All right, so hopefully you can see. Again, if I say I'm seeing something, you're seeing this, and if you're not, let me know. Okay, so let me scroll down to chapter 3 now. Now, in chapter 3, we're going to talk about determinants. Okay, and there you go. Section 3.4, by the way, there are a couple of, excuse me, there are a couple of applications. So if time permits, I would like to look at Kramer's method for solving systems of equations. And once we get there, you'll see this is an application of determinants. But first, let's begin by what is the determinant of a matrix, okay? Now, I could be writing these, folks, but if it's okay, I'm just going to go over the book, but I'll go very slowly in case you have to read it or whatever. Remember, you can get screenshots too if you like, and then just annotate later. However works for you. So let's begin with what is even a determinant. Now, the determinant, this is the definition of the determinant of a 2 by 2 matrix. For every square matrix, okay, so it could be a 2 by 2 or order 2, or it could be 3 by 3, 4 by 4. So we got to have a square matrix. Keep that in mind. So with each square matrix, there is a real number that's associated with it, and it's called the determinant. It's just think of it as a characteristic of every square matrix. Every square matrix has what we call a determinant. So here's matrix A in its most general form. It's made up of 2 rows, 2 columns. So you got your first element, A sub 1, 1, and so on and so forth. Now, the determinant of A, and there are a couple of ways you can write the determinant. I like the actual verbiage DET for determinant of A equal. This notation is very popular, but the reason I don't like it looks like absolute value, doesn't it? The reason I don't like this one is because of what I just said. It may portray or may make us, it looks as if you're talking about the absolute value of A, which is not. It's just, to me, it's a poor notation, but then many textbooks use this, including this book. But whatever it is, remember, because determinant of A is going to be a real number. So it's quite possible that determinant of a matrix would be negative. So remember, don't take absolute value. It's just a poor notation. So determinant of A, DETA. How is it defined for a 2 by 2? A 2 by 2 is actually pretty simple. So if you were to memorize, which by the way, you don't have to memorize the formulas in this course. So but it's good. If somebody forces you to twist your arm and you have to memorize, it's actually easy to remember or memorize this one for a 2 by 2. For a 2 by 2, what we do is you multiply the diagonal elements A11, A22. That's what this part is. You multiply the diagonal elements, and then from that, you would subtract the product of the off-diagonal elements. That would be A12 and A21. So diagonal, product of these, minus product of off-diagonals. Now, because subtraction is not commutative, we got to be careful here, folks. Don't do it the other way around, right? Because we're not going to get the same answer. You're going to get opposite of the correct answer. So it has to be diagonals multiplied minus the product of off diagonals. Okay. Now, down here, he's kind of showing you the same thing I mentioned. He's crossing these two diagonals, and that's what goes up here. And then he multiplies the off diagonals, and that's what goes in here. Again, for a 2 by 2, it's pretty easy, and you can see the examples that are down below. So for instance, look at part B. In part B, here's matrix B. It is a square matrix. Remember, determinants are not defined for other than square matrices. So for the 2 by 2, we're going to follow the script. We're going to multiply the diagonal elements. So there's a 2 upper left, there is a 2 lower right. Those multiply together, and right in here, 2 by 2 makes 4. That's this part. And then you subtract, that's part of the formula, the minus, and then the product of off diagonals, that would be the 1 times 4. And this will give you a 4, and 4 minus 4 is 0. There you go. That's all it is. Now, you may wonder, like, well, what does that 0, what does this tell me? In and of itself, it really doesn't mean anything, folks. It's just something at this point, let's call it quote unquote, something cool that we can do with the square matrix. Okay, so that's really, that's all it is for now. This is, wow, that's cool. It's good. We can do that. Oh, I didn't know that. So there you go. 0. It doesn't mean anything at this point. Look at this 7. This could be 7,000. Okay, whatever. It's just something we can do with the square matrix. Now, the way he structured this example, I like it because look at the number, the answer to determinant. It could be positive, it could be 0, and it could be negative. You see that? This one, the last one is negative. So again, the value of the determinant could be any real number. So make a long story short, it's any real number. So everyone hopefully is okay. And again, remember, please feel free to interrupt me and ask questions. So there. Now, 2 by 2, that's good. We have a formula, but what if we don't have a 2 by 2? What if we have 3 by 3, 4 by 4? And of course, remember, a lot of what we do anymore, we don't really do by hand, right? That's why I have those 2 links in Canvas they're actually programs. Nobody, folks, really does these things by hands anymore. It's more of a learning process for us to recognize, okay, so this is how it's done, but in reality, we don't do it by hand, but nonetheless, let's go through this process. So for 3 by 3 and higher order, like 4 by 4, 5 by 5, and so on, the method of the way to find the determinant is using the method of expansion by cofactors. That's what they call that. Now, of course, this is just definition of what is a minor, what is a cofactor, but in a moment, you'll see the determinant using expansion by cofactors. But before we get to the formula for the determinant, let's determine what do we mean by minors and cofactors. So again, emphasis on a square matrix. So the M for minor, the minor of an element of a matrix. Remember, A sub ij. This is an element of the matrix. So it could be first row, first column, first row, second column. It could be second row, third column. I have 9 elements in the matrix. So theoretically, I have 9 minors. Every element of a square matrix has its own minor. So what is that minor? The minor of an element of a matrix is the determinant that you get by deleting the row, and deleting the column in which the element appears in. So again, the minor of an element of a matrix is the determinant of a matrix you get when you delete the row and column in which the element appears in. So in this example that he has, not example, but what he has here, it says, for example, so let's say we have the general form of a 3 by 3. He wants to find the minor of A sub 2, 1. That means the minor of element in the second row, first column. So how do we find the minor of A2, 1 in that position? Well, if you look at, he has a vertical line through it and a horizontal line through it. That means he's deleting. He's literally taking out. He's going to delete the column and delete the row that A21 appears in. Okay. Now, when you delete the column, that means the first column is gone. You delete the second row. The second row is gone. So what's left over? We're left over with A12, with A13, with A32, and with A33. So that would be the determinant of this 2 by 2 matrix. And that's what M21 means. That means the minor of the element in the second row, first column. So it's going to be the minor of that. And of course, we'll do examples, folks, and you will see with numbers and it will make more sense. But for now, I'm just explaining the process. So there you go. That would be the minor of A21. That's what he just wanted to do. Sorry, this part. Now, he says, okay, this is just him, the author. He says, I want to do minor of A22. A22 means second row, second column. So first you need to locate 22, second row, second column. And then you put a line through it that deletes the row, second row, and the second column. You put the line through the second column. So you're deleting the second row and second column. What's left over? Well, the remaining elements are A11, and that's this one right here. The other one would be A13. That's this one right here. And we have A31, this one right there. And finally, A33. So now the minor of 22 means element in the second row, second column is going to be determinant that you're looking at. Okay. Now, everyone hopefully okay on minors. Again, please, if you have questions, feel free to interrupt me and ask questions. Now, what is the cofactor up here? The definition of a cofactor is right here. The cofactor, C for cofactor, of the ijth entry, the element. See, these, you have minor of an element and the cofactor of an element of the matrix. So what do we mean by cofactor of an element of a matrix? That's Cij. And this is what it means. The cofactor is when you multiply the minor of that element times -1 to the power of I plus j. Remember, I is the row number, j the column number the element appears in. So for instance, and you will see it right down here, right here. So let's say we want to do, he's done minor of A21, right? See, he did minor of A21. Now he wants to find the cofactor for A21. How do we do it? Well, once you have the minor, let's just multiply by -1 to the power. The role, by the way, folks, this, I'm going back up here. The role that -1 to ij plays here, -1 to I plus j, the contribution of -1 to I plus j is to assign a sign, assign a sign. So that's what it does. The outcome of -1 to any power is going to be what? Either 1 or -1. True? For example, -1 to the 7th power is -1. -1 to the 4th power is 1. So the combination of I and j, because these are, remember, these are natural numbers. The combination of I and j is going to give you a natural number. If it's odd, -1 to that power would be negative. And if it's even, the I plus j even, then -1 to that power would be even. That means 1. So let's check it out for cofactor of 2, 1. So you do -1 to 2 plus 1. 2 plus 1 is 3. And by the way, let me show you. I'm actually here now. So 2 plus 1 is 3. -1 to the 3rd power is -1. That's where he's getting this negative from, right down here at the end, -m21. What about the cofactor for second row, second column? Again, this one, the sign for second row, second column. So what do? I do -1 to 2 plus 2. And 2 plus 2 is 4. So -1 to the 4th power is +1. That's why the cofactor 2, 2 and the minor 2, 2 end up being exactly the same. So again, hopefully everybody's okay with minors and cofactors here. Now, what he's doing on the left side, he's showing you the sign pattern, just the sign. That's -1 to the I plus j part. He's showing it to you for these different square matrices. This would be the sign pattern is an alternative to this formula. Personally, I don't mind the formula myself, but a lot of people go with the sign pattern that you see. So in the case of, in the case of where you have a 3 by 3, in the case of a 3 by 3, the sign patterns start with plus, first row, first column. Remember, 1 plus 1 is 2. So -1 squared is 1. That's why it's positive. So it's going to be plus, minus, plus. And then you scroll to the next one, minus, plus, minus, scroll, plus, minus, plus. So the signs alternate. And you can extend it to 4 by 4 to n by n. So he's just showing you the signs. This is just the coefficient, -1 to I plus j, that he's shown us. Everyone hopefully okay. Okay. Now let's see. So let's do an example of our own. Okay. I'm gonna scroll down to the exercises here. Excuse me. Okay, so let's do maybe a couple of these. Okay, let me see here. So for example, let's take a look at, number 4 would be good. So I'm going to write it down. Let me switch to my OQCam. Okay. So hopefully, let me see. There you can see my notepad now. All right. Now the exercise we're looking at, we said we're going to look at number 4, right? So let me go to the page of the book. Okay. And this is number 4 now. Okay, in exercise number 4, the matrix is -3, 5, 1, 2. -3, 5, 1, 2. And let's call this A. The question reads, find the determinant of the matrix. So determinant of A, I'm just going to use the formula that we had for the 2 by 2. All right, and our formula, remember we're going to multiply the diagonals and then subtract the product of off diagonals. Okay, so let me do that. I'm going to do -3 times 5 minus 1 by 2. That's going to be -15 minus 2 or -17. It's really that simple, folks. It really is. Okay. So that's the determinant of a 2 by 2. All the other ones work the same way in that segment. So let me switch to the page of the book and maybe, how about number 12? Let's take a look at number 12. So I'm going to write number 12. And we can do, by the way, any one of these you want me to do, please, or you want us to do, call it out and we can do them. Looking at the ones that may be a little more exotic, like number 12. In number 12, we have the determinant of this funny looking symbol you see, by the way, this is Greek lambda. So we have this lambda minus 2, 0, 4, lambda minus 4. We want to find the determinant. So let me, again, switch back to my notepad. And there you go. So to do this one, we're going to do exactly the same thing. Determinant of matrix A. I'm going to put the determinant symbol in case you see it, so we don't completely forget that symbol. Is going to equal to, remember, we're going to multiply the diagonal elements. So it's going to be lambda minus 2 times lambda minus 4 minus the product of off diagonals. And that'll be 0 times 4, which is 0. So the result's going to be lambda minus 2 times lambda minus 4. Now, this business of lambda, by the way, near the end of the course, when we talk about eigenvalues and eigenvectors for a system of differential equations, we'll talk more about these, the lambdas and where they come from and stuff. But at this point, can I do the, what you call it? Sorry, folks. At this point, we just want to know, can I do the determinant? That's all we want to know at this point. Am I able to do the determinant? And hopefully the answer is yes. Now, feel free if you want, you can FOIL this, right? FOIL it out. And what do we get? We get lambda squared. The OI in FOIL gives me what? Negative, that's 4 and 2, -6 lambda plus 8. And we get this second degree polynomial, which again, later on, we'll talk more about these extensively. But that's it for now. That's all we wanted to do. So everyone okay on this work? Hopefully we're good. Okay, let's go back to the page of the book. And here we go, share. Okay, so we did number 12. Let's take a look at, trying to look and see if there's another one. Okay, the other ones are 3 by 3s, so let's hold off on that one. Nonetheless, though, let's do a minor and a cofactor. Okay, that we can do. Huh? All right. So first, I'm looking at maybe exercise. How about number 16? Let's take a look at that one. In exercise number 16, I'm going to write it down on my notepad. Number 16, the matrix is negative 3, 6, 4, 4, 3, negative 7, and 2, 1, negative 8. Okay, so that's our matrix. The question reads, find in part A all part A minors and in part B the cofactors. Okay, so that's what we want to do in number 16. So let's begin this one. I'm going to switch to my notepad and show you the details now. All right. So here it goes. We're doing part A of this one. In part A, I'm going to go ahead and go, doesn't matter how you go by row or by column, because eventually we're going to do all 9 of them, right? So let's begin with negative 3 here. Negative 3, sorry, I covered the camera. Negative 3 here. Negative 3 is in the first row, first column, right? So what I need to do is the following. I'm going to circle negative 3 here. That's negative 3. And remember, we're going to delete the row and we're going to delete the column in which negative 3 appears in. So once we delete the row and delete the column, then all that remains is this 2 by 2 matrix right down here, right? And therefore, I'm going to write the minor of 1, 1, first row, first column, is going to be the determinant of 3, 1, negative 7, negative 8. 3, 1, negative 7, negative 8. And now I remember the 2 by 2, right? That's easy to remember. Recall that's when you multiply the diagonals minus off diagonal. So I'm going to do, that's going to be 3 times negative 8, negative 24, minus 1 by negative 7. 24, double negative on 7 is 7. So that would be negative 17, right? So that's M11, minor of the first row, first column. And instead of doing all 9, because this will take time, let's do another one. And you call it out. Anyone cares to call out a row and a column, an element in any row, any column, call it out and we'll do it. Which one would you like to see? We just did 1, 1. So any row, any column of this matrix. Anyone?
Let's do 3, 3.
3, 3. Thank you. Let's do that one. Okay. So we're doing M3, 3. That means the minor of element in the third row, third column. So that would be negative 8. See, we are about to find the minor of negative 8 in this matrix. So we're going to delete the row, delete the column in which it appears in. And when we do, the remaining 2 by 2 determinant, see, this row is gone, the column is gone. That's gone. And this is gone. Literally, there you go, we delete it. So all that remains is negative 3, 4, 6, 3. It's going to be the determinant of negative 3, 4, 6, 3. Right? And then the 2 by 2 determinant, we multiply diagonal, negative 3 by 3, that's negative 9. Subtract from it 6 by 4, which is 24. So the M33 is negative 33. And again, what does that negative 33 tell us? In and of itself, nothing. It just does nothing. It's just a process. Has no interpretation. The value doesn't really mean anything. So likewise, You can do the other 7 if you like to, but that's how you work them. Now, this is part A, part of part A. Remember, there's 9 of these, so I don't want to waste so much time on that. Let's do now the cofactor for both of these. We did M1, 1, M3, 3. So we're doing portion of part B now. Let's do the cofactor for 1, 1. The cofactor of the element in the first row, first column. So that's going to be, now remember the sign, -1, raised to the power of row plus column, the subscript. That's 1 plus 1. Okay, 1 plus 1 times M11. The result of -1 to a power is always either 1 or -1. If the exponent is even, you get 1. So this is equal to M11. Therefore, the cofactor 1, 1 is also -17. What is the cofactor for 3, 3? The one above it that we just did. Well, that's going to be -1 to the power of 3 plus 3. Whatever element in the row and column combination, that's what the exponent is. Multiply by M, 3, 3. And it so happens again, because 3 plus 3 is 6 or even, -1 to even power is 1. This also turns out to be M33. But again, if we do this for like third row, first column, or third row, second column, for instance, this would be 3 plus 2 is 5, and now it's going to become -1. Okay, M33 is -33. So that's how the cofactors are. So hopefully everybody's okay on this work, ladies and gentlemen. Okay. Now, let me go back to the book. So that's the part about minors and cofactors. And the question is, okay, well, what are we going to do with this, right? Why are we doing this? So let me go back up now. Once we talked about minors and cofactors, now, there you go. So how are we to find the determinant of any square matrix? Any square matrix. So that determinant is going to be given by, let's see, right in here, definition of determinant of a square matrix. And this is what we call finding the determinant using expansion, expand, because you see you have this plus, 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 we're expanding a sum. It's called expansion by cofactors. Remember the C's? That's a cofactor, cofactor, cofactor. That's what that is. Now, the way the formula looks is that for this definition, by the way, the author says, suppose you have a square matrix greater than or equal to 2. So it could be 3 by 3, 4 by 4, and so on. The determinant is the sum of the entries in the first row. The first row of A multiplied by their cofactors. Remember, entries in the first row times their cofactors. So let's say I have a 3 by 3. The first row is going to have 3 elements, right? A11, A12, A13. So that's when you multiply A11, A12, and it goes to A13 if it's 3 by 3. N is 3 now. And then you multiply each of those elements by the cofactors. The cofactors we did in number 16. We did a couple of them. So this is one way, a way of finding the determinant using expansion by cofactors about the first row. Now, it turns out you can find a determinant using expansion about any row and any column. Okay, so you don't have to do it about the first row. In fact, let's say for the matrix that this one, his example, we're going to do his example, but different. Let's see how he's done it. It reads, let's see. And the matrix, okay, so he's already found the cofactors for the first row. Okay, that's fine. We do our own. So he's done this example before. He said, look, I found the cofactors for the first row. And the elements in the first row are 0, 2, 1. So you multiply element by its cofactor, element, cofactor, and there you go. The answer is 14. Okay. Now, let's actually do this differently, folks. You and I. I'm going to copy his matrix first of all. So A is 0, 3, 4, 2, -1, 0, 1, 2, 1. Okay. Now, choose any row, any column other than the first row. This is your call. Anybody. Just call a row or a column that you like. Your choices are row 2, 3. Your choices are column 1, 2, 3. Which one would you like to go with? Should we go with should we go with the second column? Would that be okay? Let's try second column here. Okay. Remember, he did first row. We're going to do second column. We're going to expand by cofactors about the second column, this column. Now, the signs. Remember, for 3 by 3, you start with plus, minus, plus, minus, plus, minus, plus, minus, plus. Those are the signs. Those are the IJ combination, -1 to the IJ combinations. So the determinant of matrix A is going to be, remember, we're expanding about the second column, about this column. So it's going to be the element times its cofactor. Now for the cofactor, remember -1 to a power gives you a sign. So I'm going to just copy the signs in the second column. The signs are negative, positive, negative. So I'm just going to go negative, positive, negative. That handles the -1 to the power part. And then the elements in these positions, second column, the elements are 2, -1, 0. So here is 2, -1, and 0. So far I have the elements in the second column and the sign on the cofactors. Okay, and let me just write down that we are expanding about the second column. Second column. That's what we're doing. Okay, now expanding about the second column. What we're missing now are the minors, right? So next to every one of these, each of these 3 numbers, I'm going to have a 2 by 2 determinant. Remember, the minors are 2 by 2. Okay. For minor of 2 in the first row, second column, right? This first row, second column. That's when you delete the first row. The first row, there you go, is gone. Delete it, and you delete the second column, right? The first row, second column. So you delete the first row, delete the second column. The remaining elements are 3, 4, 2, 1. Okay, so I'm going to write those. 3, 4, and then 2, 1. There you go. That's the minor of 2 in that position. Then move down to -1. For -1, down here. We're going to delete the row, right? Delete the row that -1 is in. That's the row. And delete the column. There you go. So the remaining elements are 0, 1, 4, 1. Again, delete the column, delete the row. We go 0, 1, 4, 1. And finally, for 0, I'm going to do this just so we practice with finding minors, but this one, it's okay if you just ignore it or just write, this is what I mean. If you just write 0 times minor of 0 in the third row, second column, you don't have to define this minor. The reason, because you multiply by 0, the product's going to be 0, right? So who cares? But I'm just going to do this to show you how it's done, finding the minors. So we're going to delete the row and the column in which 0 appears in. So the remaining numbers are 0, 1, 3, 2. So I have 0, 1, 3, 2, like that. And you can see now here, see that determinant, whatever, times 0 is 0. Next step, negative 2 times. The 2 by 2 determinant, remember, that's going to be 3 by 1. 3 minus 2 by 4 is 8. The middle one is going to be negative 1. 0 times 1 is 0. Minus 1 by 4 is negative 4. The last one, I just put 0. What do we get? Negative 2 times 3 minus 8 is negative 5. Negative 0 minus 4, that's negative 4 times negative 1 is positive 4. And negative 2 times negative 5, that's 10 plus 4. So there you go. The determinant is 14. Before I switch to the book, anyone has any question on how we're finding these minors or the cofactor? Anything about this?
Professor,
Yes.
I just have a question. Why are we expanding about the second column?
Oh, okay. I just wanted to show you and everyone that we don't have to expand about the first row, because the formula here is about the first row. This formula doesn't work about first column. See, that's the thing. For the 3 by 3, there are 3 rows, 3 columns. So there are 6 ways we can find the determinant. The author found it about the first row. And what did he find the determinant to be? 14, right? And we did the same thing. Let me switch to our notepad. We did the exact same thing, but we didn't use the first row, did we? We actually used the second column. We got the exact same number. So I was just pointing this out, that you can expand about any row or any column. Now, if we were to do this by hand, and in a moment, I'm going to actually go to the website, that second link in our canvas, and we're going to do this, and you're going to see, okay, well, it's kind of crazy how we do this by hand when technology is there, and you're right. But again, I just wanted to show you that there are 1, 2, 3 ways you can do the rows, 1, 2, 3 ways, 6 in total ways you can find the determinant. Now, the general rule, if we were to do this by hand, is this. You can expand about the third column. You can expand about the middle row. I picked second column. Why do you think I picked this column? Anyone? And you can kind of see that's the hint here. Because
Right.
it's because of the 0, right? See, so if we were to do this by hand, you want to expand about the row or column with the most number of zeros. Because for those elements, you don't even have to find the minors. You just say, oh, that's just 0. 0 times any minor is 0. Now, my choice was second column. Somebody says, well, why didn't you do third row? Because that one has a 0, and you're perfectly fine. That's a legit argument. You could have done it by 401. Now, just to set this one up, let's say I want to expand about the third row. It won't take long to do. The sign on the third row, the signs are plus, minus, plus. So I'm going to go plus, minus, plus. The elements are 401. Here's 4, 2 by 2. 0, minor of third row, second column. This time I'm not even going to bother with this because product is 0. And then 1 times its determinant, it's minor. Now, what is the minor of 4 in the third row, first column? So we're going to eliminate the third row. We're going to eliminate the first column, right? So the minor of 4 in that position is determinant of 2, 1, negative 1, 2. This is 2, 1, negative 1, 2. And skip the 0. We're going about 1 now. You're looking at this one. In the third row, third column. Third. So I'm going to delete the third row. Third row is gone. I'm going to delete the third column. And third column is gone. The minor of that element is the determinant of 0, 2, 3, negative 1. 0, 2, 3, negative 1. So let's do the determinant now. That's 4 times 2 by 2, 4 minus 1 by negative 1 is negative 1. Plus 1 times 0 times negative 1, that's 0 minus 2 by 3, that's 6. So I have 4 times. Double negative on 1 makes positive. That's 4 plus 1, 5. 1 times 0 minus 6 is negative 6. Negative 6 times 1 is negative 6. So I have 20 minus 6, and lo and behold, you see that? So we don't expect different answer. It's just how you go about it. So that just goes to show that, what I was saying earlier, you really have freedom on how you want to do this. You can do this about any row, any column. So is everyone okay on this? All right, perfect. Now, again, this is the hard way of doing it. I'm gonna switch and let's go to the website. So I'm gonna go change my share now. I'm gonna go to all right here, and there in here, if you click on the matrix calculator, or if you already have it up, that's what I'm going to use now. I'm not using Symbol Lab yet. I'm just using this. So I'm going to click on matrix calculator, and hopefully everybody can see that one. Okay. Now in my matrix calculator, notice I have this nice matrix A square matrix, and it's a 3 by 3. So that's exactly what we need. I'm going to put the numbers for the example we just did. 0, tab, 2 tab, 1 tab. The elements in the second row are 3, negative 1, 2. 3, negative 1, 2. And in the third row is 4, 0, 1. 4. Oops, sorry. I hit caps lock instead of tab. 4, 0, 1. Okay. And check this out. You see here, the first entry, determinant. And check it out, right down here. You see this number 14? So that's what I was saying. We really don't do stuff by hand, not in this day and age, but it's kind of good to see at least how this stuff works anyways. So any question about this, ladies and gentlemen? So are we okay on this work, everybody?
Yeah.
Perfect, thank you. So you can try any of the exercises, and you can, if you want, just to kind of say, yeah, I've done it, I've seen it, I've done it once, I know how it goes. Try to do one of these by hand, but then remember, you can verify your answers through this matrix calculator link or site. And let's just kind of finish this work off with, let me see, I want to see if I can find a good example for you. Okay. In exercise, I'm going to switch back to the book and then I'll show you what I'm looking at. I'm trying to find something that's a little more exciting here in the way of exercises. Okay. And that's all there is in this section, by the way. So let's go further south and see what we can find here. Okay, how about we can solve any of these. That says solve an equation, solve an equation. Which of these should we try? Should we go 52? Or we could do, I don't know, 58. This one looks kind of cool. Should we try number 58, folks? Let's try 58. It's a 2 by 2, so it shouldn't be too bad. Let's do number 58. I'm going to first write down, this is section 3.1 and exercise number 58. In exercise number 58, the question, evaluate the determinant in which the entries are functions. So you don't have to be numbers. They could be functions. They could be objects. They could be a lot of stuff. Determinants of this type occur when change of variables are made in calculus. Okay. And more specifically, you don't do this kind of work in Calc 1. Or Calc 2, for that matter. You usually do these in Calc 3. But let's do number 58. For us, is do I know how to do this? So I'm going to write the determinant, and then we will work it. So we have x, ln x, and then 1 plus ln of x. We just want to find the determinant, right, in number 58. So let me switch back to my notepad. And there you go. So I have written the problem now. The 2 by 2, we're going to multiply x times 1 plus x. 1 plus ln x minus x ln x times 1 times 1. Now, don't set it equal to 0, okay? We don't want to do that. We just want to find the determinant. So determinant of matrix A is. And at this point, really, all I can do is distribute x, right? Distributive property, so I get x plus x ln x minus x ln x, because ln of x times 1 is itself. Here we have a pair of opposites that add to 0, and there you go. The answer is just x. So that's how you would work this one. Everyone okay on this one? Now, if you're good, let me switch back. I want to do a couple of things first. I'm going to switch back to this one. And I had an eye on number 52. This one, the one with the lambdas. This one says solve an equation. Find the value of lambda for which the determinant is 0. You see that? So for this one, we actually want to set determinant equal to 0 now. Now, number 52, I'm going to copy it. And again, in a moment, I'll show you my notepad. So we're doing number 52, folks. So the determinant of lambda 0, 2, 0, lambda 2, 1, 3, and lambda minus 2. You're going to find that determinant. And then set it equal to 0. It says find lambda by setting it equal to 0. Okay. So now here's the decision point for you. Which row or column would you like us to expand about? You have your option. Which are the easiest ones? Any suggestion, anyone? Which row or column? Remember, the recommendation is to do with the row or column with most number of zeros. So that means I see a 0 here. We can expand about the first row. We can expand about the second column. Or I see a 0 here. We can expand about the first column. We can expand about the second row. So your choice, which one would you like us to do? Anyone? If no one has a preference for this one, just to be different, because we haven't done, let's expand about the first column. How's that? First column. Again, in the book, the formula is for the first row. We're going to do about the first column. So, determinant of A is, remember the sign that goes with the first column. Let me bring the paper down. This one. Our signs are plus, minus, plus, like that. For the first column, the signs are plus, minus, plus, right? For the first column. So I'm just going to copy these signs first. Plus, minus, plus. Plus, minus, plus. And then the elements. First row, first column. Second row, first column. Third row, first column, right? These are the elements. These are the signs, -1 to the power of I plus j's. And then each of these elements will multiply by their minors. True? For the 0, if everyone's okay with that one, remember, we're doing about the first column. I'm not going to bother with minor of 0 in the second row, first column. M, second row, first column. The reason, whatever this is, times 0 is 0. So that's why we chose that column. So all I have to do is a couple of 2x2s. So what would the determinant, anyone wants to take a shot at this one? Remember the minor of 1, 1. First row, first column. You delete the first column, you delete the first row. What would the determinant here look like? Once the first row is gone, and once the first column is gone. So here's the first row gone. And then the first column gone. This one. So all that remains, what's left over are lambda 3, 2, lambda minus 2. So let's copy those. So I'm going to have lambda 3, 2, and lambda minus 2. And the minor of 2, you delete the column, delete the row. So what's left over when we do that? We have 0, 1, lambda 3. So there you go, 0, 1, lambda 3. And now the 2x2 determinants, lambda, lambda minus 2. Minus 3 times 2 is 6. The middle is 0. The last one, plus 2 times 0 by 3 is 0, minus 1 by lambda is lambda. Okay, let's see how this is going to work out. I'm working within parentheses, the larger parentheses. So for this one, lambda, lambda, that would be lambda squared. Negative lambda 2 is 2 lambda minus 6. The binomial here, the last, 0 minus lambda, anything plus minus 0 is itself. So that's just negative lambda. 2 times that is going to be negative 2 lambda. And let's just distribute lambda here. We get lambda cubed, negative 2 lambda squared, negative 6 lambda minus 2 lambda, right? I'm distributing the lambda to the quadratic. And then negative 2 lambda. We could combine, we have a pair of like terms. When we combine those, we're going to get lambda cubed, negative 2 lambda squared, negative 8 lambda. And how do we solve this, folks? Remember, the question said, solve the equation determinant equals 0. So we're trying to now answer the question. Anyone want to chime in? How are we going to solve this equation? Any suggestions? Remember, to solve any equation without technology, we need to factor it and then use the zero factor principle. That's what we usually do in classrooms.
We can factor it into lambda times lambda minus 4 times lambda plus 2.
Thank you. Appreciate that. Excellent. Times, you said lambda plus 2. Perfect. The step in there, by the way, thank you for that. That's absolutely right. If you factor a lambda first, that's the lambda, the GCF, right? The GCF is on the outside. So what do we have left for those who need to see where he got these other two? Once you take the GCF out, you get lambda squared, negative 2 lambda minus 8, right? And that's what the lambda is taken out. Now, this one, he correctly saw that as a quadratic, and it turns out to be factorable quadratic. The factored form of this is lambda minus 4, lambda plus 2. And we can verify, right? If you FOIL this, you get lambda, lambda, lambda squared. The O and the I in FOIL, 2 lambda, negative 4 lambda is negative 2 lambda. And the L, the product of last terms, last numbers. So thank you. That's perfectly fine. And now since we have the factored form, we can use the zero factor principle. And there you have it. So there are 3 values of lambda for which the determinant would be 0. And we are done with this section, ladies and gentlemen. Are there any questions about what we have done? No, just out of curiosity, I'm gonna, and then we'll take a break. I know you're getting tired here, but let's do this together if you would, because it makes it better if we do things together. I'm gonna go back to our matrix calculator. And this is the clear button. See that it cleans it, so matrix gone. Now, I wonder if this thing is capable of handling characters. Now, I know probably lambda, I wouldn't know how to input lambda into this. Instead of lambda, I'm going to put x, okay? So I'm doing the problem number 52 we just did. I'm just curious if this thing can take a literal, instead of numbers, take literal variables. So that's lambda 0, 1, 0. And instead of lambda, because I don't know how to type in lambda in this site, I just use x. 0, and then I have 2, 2, and this one was lambda minus 2, or I'm going to go x minus 2. And hopefully, if it does, that'll be awesome. Let's see, determinant. Yes. There you go, beautiful. You see everyone right there. And that's what we got. I'm looking at my notepad. We got lambda cubed before we set it equal to 0. I have lambda cubed, negative 2 lambda squared, negative 8 lambda. Perfect. So yeah, even we can do that. And then perfect. So that actually confirms that we're doing this correctly. Beautiful. So what do you think, ladies and gentlemen? Are we good in this section? Everybody okay? All right, so let me now switch to the page of the book. And here we are. So coming out of section 3.1, then pretty much all we did was finding determinants, right? 2 by 2, we had to use the formula. And for 3 by 3, we use expansion by cofactors. And by the way, the expansion by cofactors, it works for larger systems. So for instance, you're looking at in section 3.2, hopefully you're seeing what I'm seeing. You can see that we have a 4 by 4 matrix A, matrix B is 4 by 4. So it actually works for however many there are. However, it turns out, by the way, the expansion by cofactors, it's very costly. It's very costly. So if you itemize the cost of doing, let's say, an expansion by cofactors, I'll go to a page of the book, and you will see it's, I believe it's page 116 of the textbook, which is right in this section. So let me go to page 116 right away, and there you go. So here's what we mean by cost of running these procedures. So this is just to find the determinant of a matrix. Now, if you have a 3 by 3, the order, remember the order of a matrix is the size of the matrix. And because these are all square matrices, we just say order n. That's implied for square matrices. That's n by n. Okay, so a 3 by 3. Now here's how they itemize the cost of cofactor expansion. You're going to be doing 5 additions. You're going to have to do 9 multiplications. Now, equivalent, if you do row reduction and then find the determinant, and I'll explain why this is a better way of doing it. So we're not there yet, but the author is comparing the cost of doing a cofactor expansion to find the determinant, or whether we do a row reduction to find the determinant. Turns out row reduction, and I'll show you how, it's a better way of doing business. The business here is finding the determinant. Now, check this out. So for the 3 by 3, it really doesn't make a difference. Small systems, whatever you do, it's not going to matter much. Let's make the matrix 5 by 5. So to find the determinant of a 5 by 5 matrix, you're going to end up doing 119 additions. Another reason we never do this by hand, folks. And multiplication, you have to do 205 multiplications. In all, you're doing 300, almost 320, over 320 operations. That's the cost of doing expansion, cofactor expansion. And the 5 by 5, if you do row reduction, and then I'll show you how that's going to find the determinant, the row reduction. We haven't shown you that yet. But clearly, it's a lower cost, isn't it? 119 additions versus 30, that's a better, lower cost. 205 multiplication versus 45, not bad. And here's where the savings really mount. This is noticeable now, folks. This is just a 10 by 10. It's not huge. It's a 10 by 10, and this is mind-boggling. To do a 10 by 10 using expansion, using cofactor expansion, we're going to have to do over 3,600,000 additions, over 6 million multiplications. That's just a 10 by 10. Imagine if this thing is like 50 by 50. Or really with large data, what if we want to do this for 100 by 100, 1,000 by 1,000 matrix? It's just not practical, in other words, is it? You can see how their numbers grow in leaps and bounds, right? So look at the row reduction with 10 by 10. That's still, we can afford it. This we can afford. And here's a cool little paragraph he has. For n by n is n factorial. And remember, the factorials grow extremely rapidly. I'm sure you've done factorials in your Calc 2, for those who took Calc 2, for convergence, divergence of series and stuff. You're familiar with how factorials grow, and that's why these numbers are crazy here. So 30 factorial is this. So even a relatively small 30 by 30, which isn't large by comparison. 30 by 30 matrix, check this out, folks. This is mind-boggling. Takes 10 to 30 second operations. And then he goes here to say if a computer could do 1 trillion operations per second, it would take it more than 1 trillion years to compute the determinant of just the 30 by 30. So again, it begs the question, then, this isn't practical. Then are there better ways? There's got to be a better way, right? And the better way is indeed the row reduction. And then the LU. The LU is really a biggie here also. And you will see the reason why LU factorization is so important. Okay, so I just want to point that out. Let's go back up here. And so what are some of the operations we can do with determinants? Now, are you looking at relationship between determinants and elementary operations? Remember, there are 3 elementary operations. We can switch rows of a matrix. We can multiply a row by any constant. And we can add a constant multiple of a row to another row. Those are the elementary operations. Well, how do these operations affect the determinant as we make these moves? So let's go to this theorem. So here's theorem 3 that tells us about the effect of elementary row operations on determinants. So I'm just going to read over this theorem. So here we have 2 square matrices. Remember, in this chapter, all matrices are squared. Matrices that are not square, they do not have a determinant. So if you have square matrices, which you will, here it's B is obtained from A by interchanging 2 rows. So remember, that's our first elementary operations. How do I get B? That's when you switch, let's say, row 1, row 2 from A. How is that going to affect the determinant of B? By switching rows of A. So if you switch rows, that will cause the determinant to be negative. So if I want to switch rows, then for determinant, we're going to multiply by a negative to get the same answer as the original problem. So remember, switching rows, the new matrix is determinant's going to be negative determinant of whatever the original is. Number 2. How are we getting B this time? B is obtained by adding a multiple of a row of A to another row of A. So this is again adding a constant multiple of a row to another row. And that's what's interesting. That operation leaves the determinant unchanged. You get the exact same determinant, so that's fine. And that's why this is actually a good thing, isn't it? Because remember, we use this number 2 for adding a multiple of a row to another row. Usually we do that to get the matrix in this Gaussian form, right? Or Gauss-Jordan form. So that's good. And that's not going to change the determinant. So Gauss-Jordan operations actually are a good thing for us. Now, in terms of determinants, I'm talking here. So if matrix B is obtained by simply multiplying a row of A by constant. So remember 3 operations: switch rows, multiply a row by constant, and then add a constant, multiply a row to another. If I just multiply a row of a matrix, matrix A by constant, so for example, 5 times first row, then that's going to cause determinant of the new matrix to be constant, same constant multiple of determinant of A. Now remember, you're multiplying a single row here, a single row. So let's say I have a 3 by 3 matrix. I'm going to multiply row 1 by 2. I'm going to multiply row 2 by 3. I'm going to multiply row 3 by 4. So I've multiplied by 2, by 3, by 4. Therefore, the determinant in the end is going to be the product of 2 by 3 by 4. That means 24 times the original. Okay, so that's what this rule 3, that's how it works. We'll see examples in just a moment, folks. So everyone, again, hopefully okay on this theorem. Again, this is the effect of doing elementary row operations on determinants. If you switch rows, you got to remember that just changed the determinant from whatever it was to opposite of what it used to be. Okay, and we'll skip this part. Now, just as we have elementary row operation, this is for the sake of determinants, by the way, folks. We don't solve systems. Ordinarily, like remember, we've done up until this evening, we never did operation on columns, right? Those elementary row operations were just that. So, but for the sake of determinants, we could perform elementary column operations now. And they pretty much work the same way as elementary row operations. Okay, and let's go, I'm trying to show, there you go, right in here. They're right up here. So if you switch columns, look what happens to this matrix. So he wants to find the determinant of this 3 by 3. What does he do? He interchanges 2 columns. If he does that, that will cause a negative here in front. You see that negative in front? That's what this is. Because he switched 2 columns. Well, same thing happened if he switched 2 rows. Okay, and then what? He says, I'm going to let's see, he factors out of the first column. So here's the first column, 2, 4, negative 2. And he moved a 2 out of it, right? He factored it. So it's now 1, 2, negative 1. And there you go. So this new matrix now, the determinant here, it's going to be twice. It's going to be, you got to multiply this by 2 in order to get the same results. So you can factor out, again, from a column. That won't affect the determinant because you're going to multiply this back through. Okay. So in this example, so here's matrix A. And what does he do? He says, well, so this is negative 1, 3, 5, negative 1, 3, 5. He's trying to get a column of zeros here. You see that? So how's he going to do that? To get a column of zeros, he's going to do, let's see, the first 2 columns. Okay, these 2 columns are multiples of each other, right? If you multiply the first column by negative 2, every element by negative 2, negative 2 times negative 1 is 2. Negative 2 times 3 is negative 6. Negative 2 times 5 is negative 10. So he says, I'm going to obtain this new column by multiplying twice first column plus column 2, and then replace column 2. You get 0, 0, 0 like that. Now it says you don't need to continue to write the matrix in triangular form. Now remember, when we expand, you can expand about any row and column, right? We said that in the previous section. And he says, if you expand by cofactors in the second column this time, just like we did in the exercises, you go 0 times the cofactor. 0 in the second row, second column times its cofactor. 0 in the third row, second column times its cofactor. Every one of those will be 0. So you get the determinant turns out to be 0. Now, there's a lesson to be learned here, folks. If one column, in this case, again, it was this column. If one column is a constant multiple of another column, that means these columns are really not dependent. They're not independent, sorry, they're dependent. Again, you can do twice first column, right? -2 times first column, and you get the elements in the second column. Or if you want, multiply all of the numbers in the second column, multiply by -1/2, and you get exactly the same results. The key is that you can get the numbers in one column using constant multiple of another column. That shows that there are dependencies between the columns, and therefore the determinant will be 0. Same thing will happen if one row is a constant multiple of another row. Same thing happens. Now, check out this matrix. The first row, -1, 2, 2. If I multiply the first row by -3, what do I get? -3 times -1 is 3. -3 times 2, that's -6. -3 times 2, and we're multiplying by, remember, we're multiplying by 3, sorry. So again, -3 times 1 is 3, -3 times 2, -6. -3 times 2 is -6, so it's not 4, that's fine. So first, row 1, row 2 are independent. Now, let's see, there should be dependencies here too. One row could be written as a constant multiple of another somehow here. Okay, because this happened in the columns, will happen in the rows. When we go to Gauss-Jordan, we'll see this. But anyway, so these are the effects on the determinant of elementary row operations. Now, the last thing that's in this section, I believe, is this one, and we're done with this section. Now, we're looking at the condition that yields a 0 determinant. How can the determinant be 0? Remember up here, determinant is 0, right? In his example, how can determinant become 0? We clearly saw this, right? One column was a multiple of another column. Let's check it out here. So if A is a square matrix and any of the following condition is true, then determinant is 0. Let's see. If you have an entire row or entire column consisting of zeros, there you go. And again, when that happens, that's the sign that there are dependencies between rows and columns. So if you have an entire row, entire column of zeros, then determinant will be 0. The other condition, how else can determinant be 0? 2 rows, 2 columns are identical. Okay. And because if they're identical, remember, you can simply subtract one from the other, and what's going to happen? We get number 1. You get 0. And finally, number 3 is when one row or column is a multiple of another row. So the things that we just observed up here, that's what we're talking about. So hopefully everybody's okay on this work. Any questions, anyone? Are we okay? All right. If we are good, let's continue on. And I think that was about it, about in this section. Now, one thing, by the way, here. Let's say in this example 6, we want to find the determinant, right? Something we could do, because remember the cost of doing expansion by cofactor expansion, it's going to be very costly, right? For a 3 by 3, for remember 10 by 10, millions of operations, right? So one thing we can help with this process is the following. We can actually do elementary row operations before we find the determinant. And by elementary row operation, notice what he's done. He's actually trying to get 0, 1, 0, 0, 0 here. You see that? This column is perfect column to expand about, do a cofactor expansion about this column, second column. And then you can reduce this and now maybe do a cofactor expansion about the fourth row. You see that? So we could make these things go a little faster by doing elementary row operations on them beforehand. And that's just something to point out. So having said that, let's actually take a look at some of these exercises. Now, again, I'm just going to randomly pick exercises that are like your homework problems, but please, if any of them you want to see, just call it out and I'll be happy to look at them together. We'll check them out. Okay, so let's take a look at the early exercises. It says determine which property of determinants the equation illustrates. Okay, in numbers, let's say number 5, for example. What property this illustrates? What has he done? The determinant, this determinant says it's negative of this determinant. They're all equal, by the way. You get the same results. So he must have done something, one of those elementary row operation, where he had to put negative in front of it to compensate for what he has done. What do you think he has done in number 5? This is the original matrix. This is after he manipulated using elementary row operations, or could have been column operation, but what do you think he's done? Anyone want to take a shot at this one, number 5? Hmm? What do you think, folks? In number 5, what has he done? Well, let's look at the rows. Well, the rows clearly, every row has changed, right? So that means he must have done a column operation. So look at the first one, the 1, -7, 6, 1, -7, 6. The second column, 3, 2, 1, is now the third column. The third column is now the second column. So it looks like he switched columns, didn't he? So that's the operation he's done. He switched 2 columns. So he's done elementary column operation, switching 2 columns. Remember, when you switch rows and columns, the effect is to make this negative. So if you don't put negative here, that means you've changed the determinant from its original value to a negative value. So he puts a negative in front to make sure that that compensates for switching 2 columns. So that's number 5. Okay. Whole bunch of these are like that. Number 16. Let me. So for instance, let me see. These are numbers 1 through 20. Yeah. So what do you think, for example, in number 18 is done? This one, number 18. So here's the first row. Yeah, go ahead, please.
Yeah, it just it looks like he swapped like I think it's row 2 and 3. Like he swapped their values. So like the 0, the 5, and then the 5, 0, 1, 3, 3, 1, 4, 1, 1, 4.
Exactly. Very good. Very good indeed. Thank you, Jordan. He did. He swapped or switched row 2, row 3. And remember, anytime we switch rows and columns, you're changing the determinant from whatever it was to opposite of what it is. So to offset, so we want to maintain equality. We want to get the same answer. So he's going to put a negative in front on the right side to offset for that action. Very good. Thank you, Jordan. So for each of these, that's what we're doing. Now, number 20 may be a little more convoluted. Should we take a shot at this one, number 20? Let's see. Number 20. In number 20, it says the determinant is 0, by the way, for this one. Why do you think the determinant is 0? He hasn't done anything, by the way. It's not like, oh, I switch rows. We can't tell that, right? Because we don't see what's on the right side. Unlike number 6, number 5, number 7, 8, and so on. Question, why is the determinant in number 20 0? That goes back to conditions that make the determinant 0, right? Sorry, I know I'm moving fast. There you go. These are the conditions that yield the 0 determinant. So in number 20, we're going to look for, is an entire row or column 0? Or 2 rows are identical or columns? And is one row or column a multiple of another row or column? Okay, so let's go back to number 20. What do you think, ladies and gentlemen? Why do you think this determinant has to be 0? Clearly, we don't have an entire row of 0. We don't have an entire column of 0. So that's not the reason. Let's see, what was number 2? Number 2, are 2 rows or 2 columns equal? Let's check it out. In number 20, 2 rows that are equal means identical. I don't see identical rows. If you do, let me know. And identical columns, 4, 9. No, to be identical, if it starts with 4, this should start with 4. So there you go, 9, 9, 3. Oh, they're not identical. Would you agree we do not have number 1 or number 2? Now, the determinant is 0, so number 3 should be what's going on. Number 3, that means one row, perhaps one column, is a multiple of another row or column. Let's see if we can figure that part out. Can you see a row or a column be a constant multiple? Means you multiply the column or a row by something, and you get exactly the same entries. If we do, then that's why the determinant is 0. So how do you think, number 20, what is the operation here? Any suggestion? For example, let's see, we got 1, 2, 3, 4, 1, 2, 3, 4, 5 columns here, right? In number 20. If we multiply, say here's 9, 3, -1, -3, 4, 12, 2, 6, 0, 0. What do you think is going on between the second column and the 5th column? Can we, yeah, go ahead.
Multiply the second column by 3.
Perfect. Every entry in the second column multiply by 3. Do we not get the 5th column? So that is the reason. So we can say that 5th column is equal to 3 times column 2. Therefore, one column is multiple of another column, and hence determinant is 0. Perfect. Thank you for that. Now, for These other ones for finding the determinants, well, let's see. We didn't do any elementary row operations on these, but we can actually, okay. I think I know why he has them. It says find the determinant. So if we can find them, for example, is one row identical to another row? Is a row entirely zero? Any column entirely zero? Let's kind of go through here. So for instance, I'm looking at 33 to 36. Do I see a whole row of zeros? Any of these? No. A whole column of zeros? Yeah, none of them. Yeah, none of those. Okay. So the next question might be, well, can we do a constant multiple of another row by another or another column? These only give us zeros, by the way. I'm not saying that's going to give us the answer. But we always look for things like that. So for instance, let's take a look at, I don't know, maybe number maybe number 32. Let's take a look at number 32. Now I'm gonna write down number 32 on my notepad and we'll do that one. So we're looking section 3.2, number 32. Let's see how we're gonna find this determinant. The entries are 9, 2, 4, 7, first column. -4, 7, 1, 3, 2, 6, -2, 4, 5, -5, 0, 10. Okay, I'll show you my notepad in a moment. So that's the determinant of A. Now, let's do this. I'm gonna change my share to my notepad. All right, so I copied the problem down. Now, let's try to do this. Again, I don't see any constant multiple of a row column by anything. So determinant isn't zero most likely. But let's do this. Let's create, using elementary row operation, we want to create as many zeros that we can in either a row or in a column. Okay. So for instance, see, I see that zero there. That's the guide for me. If there is no zero, by the way, it's random. You just maybe create zero here. In other words, do Gauss-Jordan, create, or just row echelon, get 0, 0, 0 like that, and then you can work it that way. And then expand about the column with all the zeros. But for this one, for instance, I see 0 in the third row, fourth column. So I would like to get this -5 to be 0, the one above that. So in other words, I'm focusing on the last column here. That's just me. Let's say student X, he or she says, well, 0 is in the third row. Sure, if you like, then try to focus on getting maybe 0, whatever, as many zeros here. So I'm going to work on the column. So for example, I know that, and the reason is again here, look at that, 5 and -5 add to 0, don't they? So I'm just going to add row 1 and row 2. When we add row 1, row 2, and replace row 2 by it. So I have 9, -4, 2, 5. That's the first row. I'm going to add 2 rows. 9 and 2 makes 11. Then adds to 3, 8, 5 minus 5, 0. The existing third row is 4, 1, -2, 0. And let's see. Can I create a 0 here? You see the 10? How can I make this to be a 0? Cut the -5, 10. Could I multiply, for example, because this is 10. Can I multiply, I don't know, a second row by 2 added to the third row? multiply, right? Let's multiply that. So here's what I'm doing. I'm doing twice row 2 added to row 3. And by the way, because we're doing this elementary row operation, we don't need to adjust the determinant, the sign on the answer, because I'm not switching rows. If I switch rows, I have to change this to a negative. But I'm not doing that. This operation keeps the determinant the same. Okay. 2 times row 2 plus row 3. That means 2 times 2 plus 7. Right? So that's going to be 2 times 2, 4, and 7. That's 11. 2 times 7, 14, and 3. Right? 2 times 7, 14, and 3. That's going to be 17. 2 times 6, 12. 12 plus 4, 16. 2 times negative 5, negative 10 and 10, 0. You see how that worked, folks? Okay, and now all I have to do, because I created as many zeros as I can, at this point, let's expand about the fourth column. Expand about the fourth column. So the fourth column, remember the signs, by the way. The signs go plus, minus, 2, 1. So that's going to be minus, plus, minus, plus. I'm doing the signs for negative 1 to the power of I plus j. So first row, first column. First row, second. First row, third. First row, fourth. Second row first. 2 and 1 makes 1. 2 and 1 makes 3. Negative 1 cubed is negative. So it's negative, positive, negative, positive. And for third row, first column, 3 and 1 is 4. The sign would be positive because the exponent on negative 1 is positive. And they're going to alternate. Now, you see how the columns alternate? So it's going to be plus, minus. And then the rows will alternate accordingly. So there you go. This would be the sign chart for a 4x4 matrix. We are expanding about the fourth column. The signs are, so the determinant of A is, the signs are negative, positive, negative, positive. Negative, positive, negative, positive. The elements are 5 in column, 5, 0, 0, 0, correct? Now, remember, each of these elements multiplied by their minors. So this 0 in the second row, fourth column, M2, 4. The other 0 directly below it. It's in the third row, fourth column. M3, third row, 4, fourth column. The last 0 is in the fourth row, fourth column. But I'm not going to figure these out. 0, 0, 0. That's why we want zeros there. Now you see the value of zeros. And what do we have left? Negative 5 is going to multiply by a minor of 5. The reason it's negative, by the way, negative is because of the sign here. You see that negative? That carries over here. So it's going to be 5 times minor of first row, fourth column, M1, 4. And what does minor of M1, 4 looks like? That's when you delete the first row, first column. First row, first column. So that means I'm going to have to do a 3x3 now. First row gone, fourth column gone. So it's going to be 11, 3, 8. And 4, 1, negative 2. And 11, 17, 16. Right? Now I have to find that 3 by 3. And this 3 by 3, I'm just gonna, so we don't have to spend too much time on this. I'm just gonna use software on that one. And I'm gonna share in fact with you now what I'm doing here. I'm gonna go to our matrix calculator. Share, and here I am. Let's clear this. So I'm gonna put the 3 by 3. 11, 3, 8, 4, 1, 2. Oh, sorry, negative 2. 4, 1, negative 2. Third row, 11, 17, 16. And 16. Okay, that looks right. Please check in case I made any entry error. I think it looks right. And I'm going to do the determinant. Boom. And here you go, 748. So it's negative 5 times 748. Let me grab a calculator. And I'm going to do 5 times 748. The answer to the determinant is negative 3,740. And remember, we don't interpret those numbers, right? So I have no idea what that number means. We can find them, but at this point, we just say, yeah, that's cool. We found it, and that's what it is. Now, let me, change my share, and I'll show you what I just did. There you go. So the number I got from the computer, from that matrix operator, I wrote it here times that. This is what I got. Now, let's just check to make sure we did this right. I'm going to put the original matrix now in a computer, something we could have done from the get-go. But let's clear this. Let's add. Now I'm going to do the determinant of a 4 by 4. 9, negative 4. I'm inputting the original matrix. Just want to make sure the answer we got is right. 5, oops, sorry, that's negative 5. And I have 4, 1, 4, 1, negative 2, 0, 7, 3, 4, and here I had a 10. And let's go determinant. And there you go, folks. Right down here. You see that? So it looks like we did it right. Perfect. Any questions again, ladies and gentlemen, on what we have done here about finding the determinant? If you're okay, then that's as far as the extent of what we want to do here. Don't worry about these other parts. And then we go to section 3.3, which will be the last section for the evening. So again, everybody hopefully okay. If not, please let me know. Section 3.3, we're going to look at some of the properties of determinants now. Not the effect of elementary row operation on determinants, but how about some of the properties of determinants amongst themselves? So let's go with theorem 5. For instance, what is the determinant of a product? So here we have two square matrices, same order, right? You cannot do for the case of determinant, I cannot do a 2 by 2 and a 3 by 3. So it's got to be both 2 by 2, 3 by 3, 4 by 4, whatever, same order. Then the determinant of a product is equal to the product of determinants. And the proofs are here, by the way, if you're interested in that. But we're just going to remember these theorems for what we want to do later. So remember, determinant of a product is product of determinants. Theorem 6. The determinant of a scalar multiple of a matrix. So here I have a matrix, square matrix A. Okay. And C is a scalar, like 5, 7, 10, whatever. This time we're multiplying C by a matrix. Remember, when you multiply a constant by a matrix, excuse me, we multiply every element of that matrix by the constant, right? So in terms of determinant of just A, because every row now is being multiplied by C, right? CA, every row of A is being multiplied by C. So how does that relate to determinant of just A? Well, once you multiply the matrix by C, I can remove C from every row of that matrix. So if there are n rows, I'm going to have n C's, right? And let me go to my notepad and write this one for you, just to make sure I'm explaining this to where we follow. So here's what we're saying. The determinant of CA is C to the n determinant of A. This one. So here's an example. Let's say I'm going to do 5 times this matrix. 1, 2, 3, 4, 5, 6, 3, 2, 1. Okay. So that's C is 5. I want to find the determinant of this. Well, let's multiply 5 times every element of this matrix. So I'm going to have to find the determinant of this matrix. I'm going to multiply everything by 5. 5 by 5, 5 by 1, 5 by 2, 5 by 3, 5 by 4, 5 by 5, 5 by 6. The third row, 15, 10, 5. Right? So that's what I want to find. Now, remember, this is your A, the original matrix before we multiplied it by a scalar. Now in here, to the right, I'm going to factor the constant from the first row. And remember the properties of determinants. You can, if you have a constant multiple of a row, you can bring the constant out. Oh, I'm sorry. Let me not put C. I'm factoring a 5 from the first row. Okay. So it's going to be 5 times the determinant of from the first row. I'm going to get 1, 2, 3. Then I have 20, 25, 30, 15, 10, 5. Next, I'm going to factor from the second row. Factor of 5 from the second row. First row, don't do anything. Factor of 5. So I'm going to get 4, 5, 6. And I still have the third row, 15, 10, 5. Let's factor a 5 from the third row now. So here's another 5 factored, this time only from the third row. So here's my first row, 1, 2, 3, 4, 5, 6, and there's going to be 3, 2, 1, isn't it? Factor the 5 out. So I have 5, 5, 5. Isn't that 5 cubed? Times determinant of A. So this is what we just did. We just did determinant of 5A. And the answer is going to be 5 cubed determinant of A. And everyone okay on that example I have? Now, if you're okay, let me go back to the book. And there we are. So that's what this says. See, I'm trying to clarify what does this mean. So hopefully everyone's okay on this work. And he pretty much, he kind of does his own example too, you can see. So this is matrix A. And he factored a 10 out, right? And what is he doing here? And 1, -2, 3. Oh, this determinant, he says this determinant is 5. Okay, now the determinant of the original A is going to be 10 cubed because he factored the 10, remember, from every row. So it's going to be 10 cubed times this matrix. Oh, I'm sorry, this matrix. And the determinant of this matrix is 5, so you get 5,000. Okay. And let's see what else. Now, theorem 7, determinant of an invertible matrix. Okay. Now, this is actually an important theorem. All theorems are important, but this is specifically is important because we're going to actually, remember last week we had a list of 5 things. This says these statements are all 5 true or all 5 were false. We're going to see those 5 statements in a moment. We're going to add one more to that statement. This is the determinant of invertible matrix. Now, so suppose you have a matrix A that is invertible. Remember, invertible means its inverse exists. Therefore, if it's invertible, means non-singular, the inverse exists. It says this one is invertible if and only if the determinant is not 0. So that's the takeaway from the determinant. Okay. So a matrix is invertible if its determinant is not 0. And remember what made the determinant 0 before? For example, you have a whole row of 0, a whole column of 0. One row is a constant multiple of another. Those matrices have determinant 0, and none of those are invertible. So this is an important theorem for us, and let's look at this one. What is the determinant of A inverse? You can find determinant of A inverse by doing 1 over determinant of A. That's another property of matrices and their determinants. And there you go. This is what I was talking about. Last week, we talked about these 5. Okay. This evening, we're adding number 6 to it. So notice if a matrix is invertible, its determinant cannot be 0. Cannot. So one way to see if a matrix is invertible is quickly calculate the determinant. If it's 0, say no, not invertible. Sorry, can't find it. All right. And now, the relationship between the determinant and the transpose of a matrix. This is pretty cool. The determinant of a matrix and its transpose are exactly the same. Exactly the same. So here's his example. He has a matrix A. Its determinant ends up being -6, and the details on how he did it. Now, the transpose of A, as remember, that's when you make the rows, turn them into columns. So 3, 1, -2 becomes 3, 1, -2 column. 2, 0, 0, second row becomes second column. So that's the transpose. And then he finds the determinant of this matrix, and lo and behold, you get exactly, you see that? 2, -1, 3 happens down here too. So we get exactly the same thing. Okay. And that's it on this section. So let's take a look at, so we are 9:46. We still got, can I still have you for 10 minutes, everyone? We still got 10 minutes here. So let's actually do something that we can do within 10 minutes. We can do at least a couple of these. So let's do this. Number 4. Let's do number 4. This one. In number 4, the question. It says find determinant of A, determinant of B, and then A times B, and then the determinant of A times B, and verify the product rule that the determinant of AB is determinant of A times B. So for instance, yeah, for number 4, I'm going to cheat here a little bit. I'll tell you what the cheating part is. It's nothing bad, folks. The cheating part, we're going to use that computer to do this. So we don't have to do this by hand. So I'm just writing number 4 down. I have 2, 1, 3, 0, negative 1, 1, 1, 2, 0. B is, and by the way, because you see I'm using software almost every evening that we're together. So you're welcome to use software also on your exam, by the way. So that would be only fair. Okay, so we got that one. I'll show you my notes in a moment. All I did right now is I just wrote A and B, that's it. So now let me see. Part A, determinant of A is. Part B, determinant of B is. Part C says find the product matrix AB, and in part D, determinant of AB. Okay. Now I'm going to, here's the cheating part. Okay. Don't tell anyone we're doing this. There. So I'm going to this matrix calculator. We're doing 3 by 3. So let me clean this, reduce the order. It's a 3 by 3. So I'm going to type matrix A in the exercise. It was 2, 0, 1. 1, negative 1, 2. And then 3, 1, 0. Please verify. I think I got it right. Okay, let's find the determinant. Boom, right here. 0. Cool. So when determinant is 0, that means one row or a column is a constant multiple of the other, folks. That's what that means. So we could search and see which one, but don't worry about it. But that's just the interpretation. And make sure I input these correctly. Yeah, they look good. Now, I'm going to input matrix B next to that. I'm going to go to the right of it. 2, negative 1, 4, 0, 1, 3. And then 3, negative 2, 1. Now, for this one, matrix B, let's do the determinant. And this is the determinant of that matrix. Turns out to be negative 7. Good. Now, matrix AB, I'm doing part C. Matrix AB, right in here, A times B, multiplication. We have A, we have B, why don't we multiply them? And beautiful, there you go, up here. That's the product matrix. I'm gonna write this matrix down, this one. So the product matrix is gonna be a 3 by 3, 7, 8, 6, negative 4, negative 6, negative 2, and 9, 3, 15. Okay. And then now I can clear this. Let me clear this one. Now I'm just going to copy these numbers. Remember, this is the product matrix. So I'm going to go 7, negative 4, 9, 8, negative 6, 3, and 6, negative 2, 15. Got it. Looks good. And let's find the determinant of this. And 0. All right. Now, let me go back to my note right in here and show you what I have written. So there, I pretty much copied as I was typing in. I kept track of this information. The determinant of A was 0, B was negative 7. the determinant of AB is 0. Now, remember, the theorem said determinant of AB is determinant of A times determinant of B. Determinant of AB, we just showed that's 0. Determinant of A, 0. B, -7. 0 equals 0. Checks. So that's what that exercise was calling for. It said just verify that that's what that is. Is everyone okay on this work? The one we just did? And if we are, let's see, 9. I'll do just one more, I promise, then I'll let you go. Okay, sorry to keep you. Let's do number 26 here. Again, I'm bouncing off of your exercises. Number 25, I think you're doing. Let's do something that's not gonna take time. Number 26, and you can try these other ones. In number 26, this one we're doing. The question, find the determinant of the inverse. Okay, and then it says, begin by finding the inverse and then evaluate the determinant. Okay, verify your result by finding determinant of A, and then instead of finding the inverse, then doing the determinant, it says use this shortcut. So let's see, number 26, again, I'm writing it down first, 26, matrix A, 2 by 2, 1, 2, -2, 2. And we want to find A inverse and the determinant of A inverse. And we want to find A inverse using 1 over determinant of A. All right. So I'm going to go back to, let me change my share. I'm going to go back to that software. Going to make it quick. All right. This time, clear, go down to a 2 by 2. So let's put the matrix 1, -2, 2, 2. Let's find the inverse first. Boom. So here's the inverse. And the inverse is what you're looking at. It's 1/3, 1/3, -1/3, and 1/6. Okay. Now, let's find the determinant of this A, matrix A. The determinant of the matrix A is 6. Now, let's do A inverse again. That's A inverse. So let's find the determinant of that matrix. So I have to type the matrix in. It won't take long. 1/3 tab, 1/3 tab, -1/3 tab, and 1/6. There you go. The determinant of this matrix is 1/6. I'm writing this information on my notepad. I'll show you. Now, let's do this. Now I can share with you what I have so far, and then we'll be done. All right. So I just copied that's matrix A. That's the inverse. Determinant of A was 6. Determinant of A inverse was 1/6. Now, the question was asking to find this in part A. Find the determinant of A inverse. So that's the answer, 1/6. And then it says verify the theorem. We didn't have to do it this way. It says use 1 over determinant of A. Determinant of A is 6. And there you go. You get the exact same match. So that's all you have to do on this one. Okay, and I think this is good. I don't want to wear you out too much. So let me stop the recording first of all. We're done. And